Hello, my name is Josh Lopez,
Hi, I'm Carter McMahon.
Lorenzo Nino.
and this is our presentation on the HVAC efficiency project. For this first portion, our project focuses on the predicting HVAC energy consumption in buildings, specifically heating and cooling loads using machine learned techniques. This goal is to help optimize energy efficiency by using real building data. To get started, we looked into some literature that shows us how data-driven methods can predict energy use some accurately compared to traditional models. So residential, as you can see right here, residential HVAC energy consumption is hard to reduce due to complex interrelations between factors such as building materials, tenant behavior, weather, and equipment efficiency, and then as well as a promising approach uses machine learning modules like random forest, which combine sensor data and historical records to produce more accurate predictions. The RF model has demonstrated good accuracy with R squared values close to 1.0, indicating a strong model for predicting heating and cooling loads in real buildings. Now we can move on to how we implemented prediction models. So here for this data, we imported necessary libraries using pandas to manage the data and sklearn for building and training our machine learning modules. We loaded the dataset using pd.read_csv. This function imports the data from the CSV file into the pandas data frame, which essentially is a table where we can easily work with the data. Our dataset has 767 entries, each representing different building characteristics such as wall area, surface area, roof area, overall height, and relative compactness. And you can see the data right here. After loading the data, we remove any irrelevant columns like unnamed columns using df.drop, as you can see right here as well, leaving only necessary features that target variables, heating, and cooling loads. This cleaned up the data, and is what we use to train our model.
Hi, I'm Carter, and I will be talking about the preparation, model training, and predictions. Right, and so starting off, I'll be talking about the model building with this and how we implemented the code with sklearn and using the data given. And first off, we separated the data into features X, right, as you given here, and the targets Y. And the features are the building characteristics like wall area and the glazing area. And the targets are the heating and cooling leads, which is the final thing that we were looking for right here. This is our models. And we select the relevant columns using the X and Y's as given. And and then we split the data up. And when we split the data up into training and testing sets with the train_test split code, we realized that this was an important step and it allowed us to train the model on one portion of the data and test its accuracy on another portion, ensuring that we can generate well-to-new unseen data and create the heating load and the cooling load models, as you hear, as we can print. And to train the model, we created two linear regression models, and right here, as you can tell, and one for predicting heat load, another for predicting cooling load, and finding the relationship between the input features and the target variable in a straight line form. With that, we trained the models using the model.fit and made predictions using the model.fit code again. And then once we had the predictions, we evaluated how well the model was performing by testing and controlling the different values. And with that, we can see the heating load with the MSE, RSME, and R squared score and how they differ. And as we can tell by this, the cooling score is a lot more on MSE, a little bit more on RMSE, and then it was lower on the R squared score. And with that, the model's power was strong, particularly when it comes to heating and cooling loads that use architectural elements. But according to the R squared, the models account for a significant amount of the variation in energy loads. Because of the comparatively low RMSE values, as you can tell by the 2.9 and 3.47, the prediction errors were not significantly high. And in general, the models work well, although they could be further enhanced by future engineering with the code or better HVAC models.
All right. Lorenzo Nino, and I'll be talking about the model evaluation and output interpretation and conclusion. So right now I'll discuss how we evaluate the model's performance and interpret the results. Right here, we are evaluating the model, and when we evaluate our models, using the mean squared error. And the root mean squared error and the R squared scores over here. We use these metrics to tell us how accurate the model's predictions are. And the MSE shows the average squared difference between predicted and actual values. The RMSE puts its error back into the same units as the data, and the R squared shows how well the model explains the variability in the data. And here's what we find, that the predicting and heating cooling load and the new observation and retrain model, the new observation added and the models were trained, and the new data set size, which we got to 766 and 10. Updating the model, we finally can update our models by adding the new data using the add observation and update model, and this allows us to improve it as it learns from more real world data. In summary, we've built 2 models to predict the heating and cooling loads using machine learning. By training on building features, we can estimate energy consumption with good accuracy. This project shows how data-driven methods are becoming more effective than traditional models in predicting HVAC energy efficiency, and this work has the potential to optimize energy efficiency in buildings and help reduce cost. Thank you for listening.
Once again, my name is Josh. I did the introduction, the literature research, and the data loading.
Hi, I'm Carter, and I covered the feature preparation, the model training, and the prediction, starting from splitting the data and the training of the models at the preparation step.
I'm Lorenzo Nino, and I handled the model evaluation, the output interpretation, and the conclusion. Thank you.
So, hello.
Bro, Josh, we got 30 minutes.
All right, bro. Hello, my name is Josh Lopez. Hi, my name is Josh Lopez. Bro, come on, bro. What the fuck? I locked in, bro.
Dude, I heard a little squeal, bro. That was a fun.
All right.
Bro.
That's right.
Hi, my name is Josh Lopez.
My name is Fuck,
Bro, lock in, bro.
You went second. You go
Oh, yeah, I'm
second.
second person. You're right.
You go
I'll say
second.
it.